First of all, it's a privilege to be asked to be part of this session. As Tom mentioned, I've known Mike now since about 2007. I finished my undergraduate degree at UMB. That's when Mike really gave me the concrete bug, which sort of led into my master's PhD. I loved it so much that I stayed on for another few years to do a postdoc, and then sort of in recent years made the transition from academia to industry, and now with WSP. I can sort of speak for many former students of Mike's and certainly colleagues now that, something that all students look forward to on an annual basis was our trip to Treat Island. If you attended this morning's session and this afternoon sessions, certainly you'll learn, or you would have learned this morning and later today, that Mike certainly made a number of contributions to our industry. And I think that sort of concrete exposure sites would be certainly one passion of Mike's. And really that hasn't changed between 89, a picture of Mike there at BRE. And then in 2009, 30 years later, took this picture on our way to Treat Island. What has changed in this time is you can see Mike Thomas wearing a tie here at BRE. I've never seen Mike wear a tie in the past 15 years, but what hasn't changed is certainly his passion for exposure sites, and certainly helping sort of the industry and sort of providing a central database for benchmarking accelerated laboratory test methods as presented by Benoit and Jason this morning. Also validating sort of a lot of this data that's Mike's able to publish over the past 2 decades has allowed us to sort of validate and calibrate service life prediction models. And certainly a lot of this work that Mike sort of published over the past 2 decades has also allowed sort of for advancements in standards and specifications. And certainly Mike's heavily been involved with sort of CSA here in Canada, ASTM, ACI within the US, and certainly other organizations around the world. And through all this work, sort of, we're fortunate now to have concrete exposure sites all over the world. And here I've sort of only shown a few, but it seems that sort of on an annual basis, there's new exposure sites popping up all over the world, which is really invaluable and sort of generating a lot of long-term durability data, which is really needed. So sort of as I mentioned, all former sort of students of Mike's at UMB really had sort of some sort of project that dealt with the performance of concrete exposed to harsh marine environments. And in order to sort of allow for us to study this, we all place specimens on Treat Island, and the majority of this presentation today will sort of be sort of highlighting a lot of the work that Mike's done for the past two decades, but also sort of a lot of work that's been done on the island in the past 8 decades, dating back to the 1930s. So Treat Island, if you've never heard of it, it's a sort of world-renowned concrete exposure site. It's located just east of Bangor, Maine, approximately 2-hour drive south of Fredericton, New Brunswick, where Mike is a professor at the University of New Brunswick. It's located off the coast of Eastport, Maine, and has a fairly storied history dating back to the late 1700s. In the 1930s, it was acquired by the US government in the development of what was known as the Passamaquoddy Bay tidal project. So the goal was to construct concrete dams between all of the islands, and this would generate approximately 3 billion kilowatt hours per year due to the tides, which in the Passamaquoddy Bay, which run in the Bay of Fundy, are world-renowned as the highest tides in the world. Now, a year later, in 1936, this project was scrapped. However, the site to this day sort of remains as a concrete exposure site, which is operated by the US Army Corps. Now, today, Treat Island attracts concrete nerds like ourselves on an annual basis, but also sort of avid hikers and kayakers. There is sort of a trail network that runs around the island, and you can faintly see it, but one dam that was sort of built as part of the Passamaquoddy Bay tidal project was between Treat Island, which is the large island, and Dudley Island. You can sort of faintly see it between these two islands. So in 1935, the development of this project, Treat Island was sort of used as an exposure site to sort of study potential candidate mixtures to be used for the Passamaquoddy Bay tidal project. However, after this project was scrapped, fortunately, it's been sort of maintained for the past 8 decades. Now, on days when we can't access the island, Passamaquoddy Bay is home to some great some great deep sea fishing. And certainly after a long day on the island, there's nothing better than some North Atlantic marine lobster and seafood. And the hospitality is second to none if you're ever fortunate enough to be sort of in Eastport or have the opportunity to visit the island. Now, Treat Island, as the name implies, is an island. The only way to access the island is by boat, and Captain Butch Harris and his father have been taking researchers out to the island for the past sort of 50 plus years, and he seems to have a boat for the job. Picture here of Mike in 2019 when we delivered some cylinders to the island. Now, if you've seen or if you haven't seen pictures of Treat Island, 15 to 20 years ago, it looked like this. Unfortunately, I'll show you a few pictures in a few slides. Unfortunately, it's not as pretty these days. However, a significant amount of research now is mostly done sort of on the beach and a section of this mid-tide wharf as well. So Treat Island is known as a very harsh marine environment. It's exposed to the highest tides in the world, ranging anywhere from sort of 20 to 25 feet, moving this elevation every 6 hours. It's a very harsh marine environment, depending on sort of where concrete blocks are located on the island. It's exposed to 100 to 160 freeze-thaw cycles per year. Water temperature is really maintained around 5 degrees Celsius. So other than sort of freeze-thaw and chloride ingress, concrete's exposed to wet-dry cycles, abrasion, erosion, chemical attack by marine salts. So pictured here at low tide, as the tide increases, you can see this is a slightly rainy day, but these mid-tide specimens have been submerged, and the tide will continue to rise sort of upwards towards the bottom of this blue tarp. Unfortunately, the mid-tide wharf sort of has seen better days, but fortunately, a lot of these specimens at the tide wharf have been retrieved, and a lot of durability data has been published. This is sort of pictures of what the mid-tide wharf does look like now. Fortunately, however, a lot of work is being done on the beach, as you can see in the top right hand of your screen. Unfortunately, there is, though, a large section adjacent to sort of this deteriorated wharf, which is home to a lot of specimens. So I'd like to sort of briefly sort of touch upon a lot of the research happening on Treat Island that sort of happened sort of over the past 8 decades, but also a lot of research that Mike has been involved with lately. So certainly 8 decades, as you can imagine, I mean, a number of researchers looking at a number of parameters. Here I've listed, I mean, just a few of them. Certainly a large part of sort of Mike's contribution to Treat Island has been looking at the effect of SCMs and ASR, and I'll be sort of briefly sort of touching upon those in this presentation. To give you an example of how harsh an environment this is, if you've seen Mike give a presentation on Treat Island in the past, he's much funnier at explaining these pictures than I am, but I'll try to do my best. Pervious concrete, probably heard of it, pervious or permeable concrete. When it rains, it drains. These are specimens that were placed in 2006. So these are fairly large prisms, 6 by 6 by 21 inch prisms. They're not just going to float away. In 2007, upon revisiting the island, really that was nothing left of them. All that was left was this sort of 1 or 2 inch small little specimen. So makes you sort of rethink whether or not you want to use pervious concrete in harsh marine environments exposed to freeze-thaw. What I will be sort of talking a lot about in this presentation in a few slides is a lot of work as part of a CanMet research project that was initiated between sort of 1978 and 94. And Mike sort of led the retrieval effort in 2003. So between 78 and 94, approximately 350 concrete specimens were placed on the mid-tide wharf. There sort of used to be sort of research usually come out and used to label all the specimens. In 2003, sort of Mike led an initiative to retrieve a lot of these specimens and sort of study the durability performance of a number of these specimens following 25 years. Before I get to sort of that, I'll just talk about some other research that sort of Mike's been involved with on Treat Island. Certainly, as it was discussed this morning, certainly a lot of work on ASR. To date, there's been 4 series of research blocks placed on the island. In 94, 12 blocks. Looked at the effect of more or less supplementary cementing materials. In 2018, we achieved 6 of those blocks, and sort of that work is underway to sort of publish those results hopefully shortly. Three other tests or 3 other projects or phases resulted in blocks being placed in 2003, 2006, and 2016. And these are really part of greater research programs where specimens were placed at Treat Island, the Canyon Exposure Site in Ottawa, Ontario, as well as University of Texas in Austin. In 2016, these 5 blocks here were part of a larger project. All these blocks were cast in Portugal, looking at the effect of fly ash, and these specimens were placed on a number of exposure sites in Portugal, Norway, Iceland, Germany, Canada, and then here at Treat Island as well. And then, as Jason mentioned this morning, if you were able to attend the session this morning, the project that they're working on, the NCHRP, will result in approximately 24 blocks being placed in the coming year or so. So I won't be showing sort of any expansion data, but one of the questions that was raised this morning in one of the sessions was sort of what's the effect of freeze-thaw and ASR. The picture isn't too big, but this little piece here is more or less the size of a bowling ball, and this is sort of just the effect. This is a control mixture without SEMs, and more or less shows sort of the effect of freeze-thaw and ASR. So this bowling ball shaped specimen used to be sort of the size of a regular block. However, sort of as a result of ASR and freeze-thaw, 15 to 20 years later, it's more or less disintegrated. So as in all specimens placed on Treat Island and certainly exposure sites around the world, all these specimens are embedded with steel gauges, or embedded PIDs, sorry, which allow for expansion measurements on an annual basis to take place using a DMEC gauge. And Jason Heidecker here on the left with Rachel Lute conducting annual expansion measurements. Other work that's happened on the site includes the effect of cracking on corrosion. So these specimens are placed at the high tide level in order to promote the presence of oxygen and moisture, constituents needed to initiate corrosion. A lot of work's being done on alternative cementitious materials, so the performance of calcium aluminate cement or calcium sulfur aluminate cement, or etchenite-based binders containing calcium aluminate cement, Portland cement, calcium sulfate, primarily looking at the durability performance of these specimens. There's also a lot of reference blocks that have been placed on Treat Island over the years. In 1997, the Hibernian oil platform. It's an offshore oil rig located approximately 200 miles off the coast of Newfoundland. At the time in which it was placed, reference blocks, more or less the size of your fridge, were placed on Treat Island, and a large corn program has taken place over the years. So this is, they call it modified normal density concrete. So the aggregate was partially replaced with a stalate, so an expanded slate lightweight aggregate. Just recently, the Hebron oil platform, again, another gravity-based oil platform, was put into service around 2018, 2019. And at the time, again, a number of large reference blocks were placed on Treat Island. In this case, they were placed at the high tide, mid tide, and fully submerged below low tide. No coring has taken place, as they were only placed approximately 2 or 3 years ago. However, they will be sort of cored in the future to determine the performance of these binders. There's also been a lot of work on ultra high performance concrete. This is sort of some of the work dating back to specimens that were originally placed by the US Army Corps and then by sort of Mike Thomas in 2006. This is work that was just published last year, which I'll briefly touch upon at the end of the presentation. It's looking at the durable performance of UHPC exposed to such an environment after approximately 20 years. And finally, a lot of work has been done by sort of certainly the US Army Corps, which operate the site, Georgia Tech, University of Maine. What I'd like to briefly touch upon, though, is the durability performance of concrete containing supplementary cementing materials. And as I mentioned, sort of a fairly large research program was initiated in 78, resulted in the placement of approximately 350 concrete specimens, looking primarily at the effect of supplementary cementing materials in sort of mitigating chloride penetration, but more or less sort of durability as a whole. And a number of parameters were studied: SEM type, replacement level, water cementing ratio, fiber content or fiber type, reinforcement type, all at a fairly constant cement content. But in 2003, Mike sort of led a large retrieval program as a lot of these phases began to reach an age of 25 years. So here, just quickly looking at the various phases, the second column presents the date in which these were placed, varying water cementing ratios, various levels of SEMs, and then sort of a few other details in the final column, looking at effective air enchainment, steel fibers, some phases contain lightweight aggregate, reactive aggregate, etc. So this sort of work began sort of in the early 2000s, once a lot of these earlier phases had reached an age of 25 years, and sort of Mike led the charge in sort of returning these specimens to UMB and sort of determining really the durability performance of a number of these binders. So research program, I mean, more or less looked like this, anywhere from a visual observation to studying both the mechanical and durability properties of these binders. So this resulted in sort of removing the specimens as pictured in the top left. This is the most work I've ever seen Mike do on Treat Island. This is Mike with a pressure washer cleaning off specimens to do a visual observation before returning them to UMB. And certainly out of all this, Mike's been sort of part of a significant amount of literature based on sort of not only sort of this project, but a lot of other work on Treat Island. And Treat Island was featured on the cover of Concrete International in 2011. So to briefly sort of summarize some of these results or some of these phases. If we look at phase one, for example, looked at a range of water cementing ratios and SEMs. Starting off, just a visual observation is typically done on a lot of these phases. If we look at sort of the top right hand, this is sort of a consistent visual rating that was used for all phases. And the rate and extent of deterioration really sort of depends on water cementing ratio and SEM, as you can imagine. If we look at sort of water cementing ratio of 0.4 in the bottom right, really we have sort of surface deterioration that's relatively low. However, as we increase our water cementing ratio and increase our slag content, and the surface deterioration increases. As part of all of these phases, a lot of work was done on determining the depth of chloride penetration. So to date, fortunately, blocks from all specimens have been retrieved, and cores have been extracted from all blocks to determine sort of depth of chloride penetration, the effect of SEMs in mitigating chloride penetration. Plotted here is chloride concentration at a depth of 60 to 70 millimeters on the y-axis. 60 millimeters was selected as it's the minimum concrete depth required for concrete exposed to chlorides in accordance with CSA, so the Canadian spec. And on the y-axis, we have all the phases, various SEM replacements, and sort of each box represents the various phases. If we only look at the controls, that is 100% Portland cement, we can see that chloride concentration at this depth is in the range of 0.1 to 0.4%. So this is well above sort of the typical chloride threshold of 0.05 to 0.1, which is sort of commonly used in the literature as the concentration of chlorides needed to initiate corrosion. So although it's been shown elsewhere that sort of reducing the water cementing ratio sort of increases the resistance to chlorides, the effect is really small when compared to using SEMs. If we look at sort of binary systems, so this is all data from blocks following 25 years of exposure at Treat Island. We can see the concentration is much lower. The majority of mixtures fall below a threshold of 0.05. And then if we look at ternary binders, again, marked reduction in chloride penetration at this depth. So really this long-term data is really invaluable, highlights perhaps some of the deficiencies of current specifications and perhaps the need for performance-based specifications. So switching gears, let's briefly talk about documents this morning. Mentioned Life 365, service life prediction model developed around 2000 by Benson Thomas. This has sort of this model certainly still used to this day, and really a lot of this data that's generated on Tree Island, but also other exposure sites, is really invaluable in sort of validating or calibrating models like 365, amongst others. If we look at phase 9, this is a 0.5 water cementing ratio, various levels of fly ash, slag, and silica fume. Again, after 25 years, we see a marked reduction in chloride penetration relative to depth. So sorry for no colors here, but this is the control, 100% Portland cement, concentration sort of well above 0.05 at a depth of 140 mil, compared to mixtures containing SEMs, which is significantly reduced. So assuming Life 365, typically assumes a surface concentration of 0.8. However, in this case, it was reduced to 0.5, and lower concentration in this case was assumed to be relatively low paste content within these mixtures, and perhaps loss of pace due to the surface during exposure. So generally, I think you can agree that the model does a reasonably good job at predicting the penetration relative to depth when compared to the existing chloride profiles, but this is certainly knowing or assuming the surface concentration in this case. However, really sort of in marine environments, this is really not always the case, or really can never really know what it is, as really depends on a number of factors: cement content, type and level of SEM replacement, exposure conditions, loss of surface to salt scaling, chloride binding, leaching, etc. However, sort of assuming a surface concentration of 0.5 in this case, Life 365 does a reasonable job at determining chloride penetration. Just in closing, I highlight sort of a few results. This is sort of work that was published last year in ACI Materials. It's perhaps one of the longest running durability projects on UHPC, especially sort of for UHPC specimens, placed on a concrete exposure site. This work sort of highlights a series of specimens that were placed on Tree Island, sort of dating back to 95, concrete produced by Whaley and Neely from ERDC, all the way up to 2004 when Mike placed specimens. So certainly slightly modified mix designs. However, you can see sort of, negligible expansion between 5 and 21 years. So again, these are all specimens placed at the mid-tide level. And if we look anywhere from 5 to 21 years, really we're not seeing penetration really deeper than 10 to 15 millimeters. And if we sort of group these together and compare them to sort of high performance concrete, which is arguably a very good concrete mixture, we can see a marked reduction in chloride penetration. So Mike sort of proposes this theory that perhaps UHPC sort of has a disconnected porosity, which results in sort of no increase in expansion from 5 to 21 years in a lot of these binders. And sorry for the small picture, but in this case, this is just an example to show sort of the negligible penetration of chlorides. In some of the specimens that were from the RPC series placed in 96, they were reinforced just to more or less show the effect of low cover on maintaining steel in sort of a passive condition. So in this case, concrete was embedded under only 10 millimeters. Certainly in sort of a conventional Portland cement base binder, this would certainly corrode in this period of time. But after 13 years at a cover of 10 mil, no signs of corrosion were observed on this steel. And all this work is published in ACI Materials. So in closing, certainly Tree Island amongst other exposure sites, and certainly sort of the work that's Mike has sort of brought to the industry over the past 2 decades, has really been sort of invaluable. There's certainly a number of lessons that can be learned from treat island and certainly sort of concrete to withstand the harsh North Atlantic environment that's found on treat island. Certainly incorporation of SEMs is needed at sufficient levels. Certainly, the use of stainless steel is an option, and certainly UHPC, has been found to perform very well. And then finally, service life prediction models such as Life365, amongst others, can to a reasonable degree predict chloride penetration. I'd like to thank you very much and close off with just a few pictures over the years. And as Michelle mentioned this morning, certainly, Mike, thanks very much for everything.